In part 6, we start looking at a meaningful way to start summarizing categorical data. So when we were talking about the binomial experiment, because that's about a categorical, specifically a yes-no, right, where we're counting up the number of successes, that number is not terribly meaningful in most contexts. If I told you that 40 students passed exam 2, you would sit there and go, well, but how many students took exam 2? And you might have a little bit more information because you're at least sitting in one of the two classes, so you can maybe infer that there's twice as many students as are in your class. But still, what would be more meaningful would be to say that 60% of students passed exam 2. I have no idea what the actual proportion is, but that's what we're talking when we talk about sample proportions. So the number in our sample over the number of people in our sample. So that's our sample proportion. We're going to talk a little bit about how this sample proportion is distributed. So we have actually seen this before when we did the last section of 5, this normal approximation to the binomial, but we're going to look at it in a slightly different context, and we'll get to revisit something we already did before. Actually, when we talked about smelling Parkinson's and Joy, that woman who could smell Parkinson's, we all put our little magnets up on the board, we were starting to look at the sampling distribution of the sample proportion, though we recorded the number of shirts that we smelled correctly as opposed to the proportion of shirts that we smelled correctly. So anyways, this is what we're going to be looking at in part 6. So we're going to be looking at the proportion for a categorical variable. And this all comes down to using the normal approximation to the binomial. So if we're talking about a sample proportion, this thing is going to be denoted p hat. Just as a note, the population proportion, the real value from the population, will be denoted with a p, just like back when we did part 3 when we talked about the the response variable. The true response variable, the one we observed, was a y, and what we predicted was a y hat. Same deal here. And if we want to calculate that p hat, that proportion of successes in our sample, we'll just take the number of successes, right, our x over our n. So we're going to change up the binomial slightly by just going ahead and dividing by the total number, so that way we're not arbitrarily saying there are 40 people passed. We're able to say 60% of people passed. And so regardless of our denominator, we know what the pass rate was. So we have a drawing here of what a number of successes looks like if we're dealing with an n of 30 and a p of 0.5, right? We can see here the mean of this thing, if we're talking about a number of successes, is at 50% of 30, is at 15. The most common thing is 15. Now, what do you think would happen if instead of looking at x, instead of having you guys put the number of shirts you smelled correctly, I had you put the proportion of shirts you smelled correctly? So if you smelled 6 shirts, you would take that and divide by 12, and you'd put 0.5 up on the board instead of 0.6. So hopefully you took a minute to think about that. But all we're going to do, the only change that would happen to this distribution, is that every single one of these things would be divided by the 30. So if 10 of the 30 came out successful, that'd be 1/3. 20 out of 30 would be 2/3. 30 out of 30 would be 100% success. And anything out here would be meaningless. And so 15 over 30, we could now say our mu of p hat, our mean for that sample proportion, we should expect to see around 50. If it's 50% success, we would expect our sample to have 50% success as well, provided that it's a well-taken sample. So should look the same in terms of shape, but centered at p instead of n times p, right? Instead of looking at the number we expected to be successful, we're looking at the proportion we expected to be successful, which is just the true population value. So we got this cute little example here. We're talking about students being asked to spin a penny and record what they're doing. So they're going to spin the penny, and they're doing this 10 times and then 20 times, okay? So in this case, our n is 10, but we're going to repeat this 200 times. So the number of students here is not our sample size, it's our number of replications. And our sample size is actually the number of times the penny was spun. So you can see in this first one, if we spin a penny 10 times, it looks like the middle of this distribution is right around 50%, what we would expect. And of course, it's possible to get a very low percentage or a very high percentage of heads because we're only spending 10 coins. Now you'll notice we don't have any out here, so it looks like nobody was 9 or 10 heads. If we don't have anything out here, it looks like nobody got 0 or 1 heads. So just pointing out that those two things didn't happen because they're pretty unlikely, right? That would be hard to get. In fact, we could even figure out the binomial of that. We could do a binom PDF. If we're spending a penny 10 times with a success of 50% because it's fair, what's the chance that you get 9 or 10 or 1 or 0? We're going to find that those probabilities are pretty low. So if we're doing this 200 times, it is quite possible we won't get those out. Now the real question is, what would you think would happen if instead of 10 we looked at an n of 20, which is what's going to happen next? And of course you guys have the lecture notes in front of you so you can see. But before you even saw that, hopefully you're sort of sitting there going, well, I'd still expect 50% heads, right? So it should still be centered at 50%. And that's what we see. It's still centered at 0.5, just like it was before. But what has changed? It actually looks like we have some less than 0.2 and less or greater than 0.9, which is bananas. That's very, very unlikely. So I'm a little confused by that. But hopefully we're starting to see that there is more centered, more of our data is clustered around the center. I couldn't think of the word. In fact, look at before, we only had 50 coming up at 40 to 50, and we had about 45 coming up 50 to 60, where now that number is at 65. So it's much, much more likely to be right around 50%. So as our n increases, we're actually seeing that this becomes less spread out. Now, this particular graph I definitely should replace because, like I said, this kind of belies what I just said. But this is a standard thing that you would see. If you take a larger sample, it is harder to flip 20 coins and get 18, 19, or 20 of them coming up heads, which is what you would need to be out here, versus getting 9 or 10 heads out of 10. So they're both symmetric and unimodal. They're both centered at 0.5. But larger n, smaller spread. And there's actually one more thing that'll happen as well with a larger sample size, and that's actually that you'll see something that looks more normal. And we talked about this when we did the normal approximation to the binomial. I did an example and I sort of said, well, we have more possible answers, so we're getting less of those big gaps between those histogram bars. So both of these things are true as our sample size increases.